Hello everyone. In this chapter, we are going to talk about Ethernet, which is the standard for LANs, local area networks. So it's also a standard called IEEE 802.3. So in this chapter, we'll talk about a little bit of the history of the Ethernet, how it began, and then we will have an introduction of this standard, and also some of the details related to how this the physical standard and also the data links layer standard related to the Ethernet. And then we'll also talk about advanced switch operation, and also finally we'll talk about Ethernet security. So Ethernet was kind of co-invented, mainly invented by a person called Bob Metcalfe. So he was working on his PhD at Harvard in the early 1970s. So his dissertation proposal in the beginning was not accepted by the supervisor. So at that time, so then he tried to look for something else to do. So at that time, so he found a job at Xerox PARC. So Xerox PARC actually was very well known, a very advanced IT company 50 years ago. So at that time, it was really like Google and Apple nowadays. But of course, we know Xerox is not a very pioneering company anymore. But at that time, it was very good at IT. So Bob Metcalfe worked at this company, and then he got a chance to visit the University of Hawaii's AlohaNet pet radio project, and he got some idea there, and then so he developed a way to make the um, kind of the network system more efficient based on AlohaNet, and AlohaNet was more or less kind of based on radio, uh, so it's not about wired cable. So Bob actually applied that system, um, applied the mechanism to a cabled network and called it Ethernet as a kind of like a joke because ether actually is a material that did not exist. So later on, Bob eventually he got his PhD from Harvard, and also a few years later he left Xerox and formed his own company called 3Com, which later would become a very successful networking company. So he commercialized the idea of Ethernet um, with 3Com and also other companies that he worked with. So now we'll give a more detailed introduction of what Ethernet is. Ethernet was created for local area networks, which are networks that operate on a customer premises or networks in your home or a network in an office. Right? Ethernet is a family of computer networking technologies commonly used in local area networks, which we call LANs, and also bigger ones like metropolitan area networks. These are called MANs. As we mentioned earlier, Ethernet standard is part of this IEEE 802 standards. So it's governed by the IEEE 802 Standards Committee. So IEEE has this IEEE Standards Association. So it also works together with ISO and ITU, which are the International Standards Organization, and also the International Telecommunication Union. So they work together on these standards, but actually most of these LAN standards come from the IEEE Standards Association. So there are also different working groups under this committee. So there's a AO2.1 working group, which are mostly working on standards used by multiple working groups. So there are the standards that are shared upon different working groups, including like the security standards, which are for both, say, wired and wireless networks. Then AO2.3 working group is for the Ethernet standards. So that's our focus in this chapter. And AO2.11 working group is for Wi-Fi wireless LAN standards, which we'll talk more in the next two chapters. So the Ethernet standard actually focus on both layer 1 and layer 2. So if we look at the table here, we can see So on layer 1, they actually define the physical layer standards for Ethernet. So like what kind of cable should be used. Also like you look at the wireless, then it define the standards for the Wi-Fi signals. And then in layer 2, they also like AO 2.3, they talk about the MAC layer standards. So and then you also have the AO 2.2 that actually defines the LLC layer, the logical link control layer, which is kind of the sub layer under this layer 2. And then for wireless, and there is also the AO 2.11 MAC layer standard. Yeah, so in this chapter, we'll focus on this part. These are for the wired local area network. And then at the end, we will also talk about AO 2.1, which is for the security. So now let's look at an example of a simple switched Ethernet network. So suppose we have an organization with many computers like this, right? Then many of these computers, like you have many, for example, employees, they are using different computers. And this computer all would have a cable connect to a switch. And this cable, that is actually the Ethernet cable, right? So that is kind of like the LAN cable, or sometimes we call it like Cat5, Cat6 cable that we are using. So the LAN cable or Cat cable, right, that we use to connect to our switch. And this switch will connect to like a larger switch, right? So sometimes we call it a core Ethernet switch. And so you have smaller switches, then they have the output cables, and this will be connected to a core switch. And then you have another core switch here, and then maybe you also have another core switch, which is even at the supposed to be a higher level, right? So this would be a simple switch Ethernet network that is quite common in an organization. So yeah, multiple core switches, and under each core switch, you may have like even more switches, right? So a core switch connects switches to other switches. So that's kind of the idea here. So this is a diagram of a core Ethernet switch. So usually it's like 48 centimeter wide and 18 centimeter to about a meter tall. So it can be very tall, right? So depending on how big it is. So again, like they could fit on a rack like this. So as you can see from the back, there are many ports. So where you can plug in a lot of LAN cables. So of course, these core switches have to be very powerful because they have to process many incoming signals and also like output them at the same time. So switches often connect to other switches through optical fiber these days, right? Because they are faster than the LAN cable, right? So usually like from the computer to the switch, then usually I think people are still using LAN cable a lot of time because it's cheaper and also easier to install. But then for switches to switches, then nowadays I think a lot of time then they can be connected through trunk links with optical fiber, but it can also be like using like a lot of cat cables. So workgroup switches then connect hosts to the network. Is like this one is kind of like a small switch with maybe say 24 or 48 ports. Then your computers, like your host, like just a standard like user computer or like a server, that will be connecting to a switch. Now of course, like this diagram is very simplified. As you can imagine, like one switch will be connected to like 20 some computers or devices. So this one is how a workgroup Ethernet switch looks like. So usually it's like 48 cm wide. So the width is the same, right? But usually it's much shorter, right? So it's much thinner It's not very thick because it's only serving not too many ports, right? As you can see here, how many ports we have. So we can like, so you have 16, 16, 16, so you have 48 ports here. Right? So it can operate much more slowly than core switches, but then still give adequate service because like compared to a switch, it does not, compared to a core switch, it does not have that many input and output. Right? So this one has 48 ports, where for core switch you may have hundreds of ports. So hosts normally connect to workgroup switches through UTP copper wiring. So UTP means unshielded twisted pair. So normally nowadays they are the CAT cables, right? So or the LAN cable. So so as I said, it's cheaper and also easier to install. So basically nowadays, like the CAT cable that you are seeing that you have been using is like UTP copper wiring. So now we'll talk about the a little bit more about the standards for the LAN cable for this physical layer in Ethernet. So the two main medium used in local area networks nowadays are UTP, which is again the CAT cables or optical fiber, or sometimes we call it fiber optic. And so this table actually compares the characteristics of these two medium. So for unshielded twisted pair, they are basically copper wire, and then for optical fiber, then it's glass. For unshielded twisted pair, the signal is electrical signal, basically based on the voltage of the electricity signal that is passing through the copper wire. And then for optic fiber, there is light. That is whether the light is on and off and so on. And the maximum distance in length, usually for unshielded twisted pair is 100 meters or lower. So that's the maximum. And then for the optical fiber in length, then usually it can be longer. It can be 200 to 500 meters. And then if it's not for LAN, then it can be even longer. And the speed actually, now that although we are saying optic fiber can be much faster, but sometimes when you compare the speed, they could be similar in terms of like when you use it for LAN. And then the cost of optical fiber is much higher than unshielded twisted pair. So that's why like for LAN, there is unshielded twisted pair is much more popular. So now we talk about data transmission. So we know data are represented in computers using binary system, so using bits like 0 or 1. So then and we want to send a 0 or 1 from one computer or one device to another device. So in binary transmission, then there are two states. Then one bit is sent in each clock cycle. So basically I'm saying the first, for example, microsecond. Then I look at this whether it's 1 or 0, and then the next microsecond, then I'll look at what signal I'm getting. Again, it could be about the voltage, whether it's high voltage, low voltage, or things like that. So we look at the clock cycle and also the signal that we are sending. So this one is binary transmission. That means you are just sending two types of signal, either 1 or 0. But then of course it's possible to encode more signals or more bits into your signals, which we will talk about soon. So in digital transmission, there are a few states. For example, 2, 4, 8, 16. Then more than one bit is sent in each clock cycle. For example, each clock cycle, I'm actually having four possible, for example, four possible levels of voltage that I can send. If it is the highest voltage, then it means 1, 1. If it is the voltage is at this level, there's 1, 0. If it is at this level, there is 0, 1. If it's at this level, there is 0, 0. So that means for each clock cycle, I'm sending 2 bits instead of 1 bit. So you look at this, it will be much faster than the binary transmission that we talked about in the previous slide. Okay, so now if we want to increase the speed of our network, right, or of a cable or any transmission media, so what we can do is, there are two possible ways to increase the beats, right? So the first one is you can use more states. So that means in each clock cycle, instead of sending a binary signal 1 or 0, you are sending multiple bits, right, that you encode in different states. Just like the previous example that we looked at, like we can encode 2 bits instead of 1 bit in one clock cycle, right? Then you can increase your transmission speed. And the second way is you have a shorter clock cycles. Instead of using 1 microsecond, you use half microsecond, or you use 0.1 microseconds, and so on. So usually people find that the latter is much easier in practice. So although like it's in some media it's possible to use more states, for example, say voltage, I can use multiple levels of voltage. But then when you increase the number of states or the encoding, people find that actually when you do that, the error rate will be much higher. So technically it's not easy to do, although conceptually you might think it's easy. So because I can have many different levels of voltage, right? For example, but actually practically is not that easy. So that's why people are trying to use shorter clock cycles. So nowadays the limiting factor on transmission speed is usually the ability of sending and receiving devices to work properly over ever shorter clock cycle times. So a lot of times actually the transmission medium, like even if we're talking about like optic fiber optic, right, or even like unshielded twisted pair, right, they are basically transmitting like close to the speed of light, so that's very fast, right? Because both are like electricity and light, they are traveling very fast in this medium. But then the problem is whether your devices, like the switches, the routers, and so on, can work properly, like to handle so many signals coming in at a very high speed. So normally, as we said, the limitation is not in the cable, but more like in the devices. But we will talk about both. So this is an example of like sending electricity signal through like copper wire. So you can represent, say, if the voltage is between 3 volts to 15 volts, then it actually represents a 0. Then if it is between -3 to -15 volts, then it represents 1. Right? Then actually the error resistance is quite high because there are a lot of times there are variation in the voltage because of like many different types of interference. So then when you just use your medium like to represent two states, just 0 or 1, then it's more error resistant. So just an example, if you have 12 volts that you are sending, but then when the signal propagates through the wire, then there's attenuation. That means the signal becomes weaker. So the final signal becomes just 6 volts. Then it's still read as 0. So there's no error. This diagram shows a UTP, the unshielded twisted pair. So just again, it's kind of a standard CAT cable. So the cable look like this. So there's the jacket wrapping around the cable. So you will cut away the connector. So usually we call this the RJ45 connector. It has 8 pins here. So if you cut it, and then you will see like there are 4 pairs of wires, and each pair is twisted like this. So each pair has 2 copper wire twisted like this. So So that's why it's called twisted pair. So and then it does not have particular shield like fold or other shield for the cable for the wires. So that's why it's called unshielded twisted pairs UTP. And this way is just a pen for comparison. So it's around as thick as a pen. So this one is the RJ45 connector that we are using with our LAN cables. And this one is the jack that you normally see on the wall where you can plug in, and of course like on your laptop computer then or your desktop computer you may also have a jack like this for you to plug your Ethernet cable in. So for the twisted pair, then you will look at one pair, then actually with each pair will transmit 1 bit per clock cycle. So if you only use one pair, then you just can transmit 1 bit per cycle, right? But of course, like what we can also do is parallel transmission. That means you do 1 bit per clock cycle per wire pair. Then if you have 4 pairs, you can transmit 4 bits per clock cycle on the 4 pairs. So this one is kind of a closer look at the UTP cables. So again, you have 4 pairs, and then for each wire actually has its specific color. So the color actually are very useful because when you need to connect this wire to the connector, to the RJ45 connector, or um on the wall jack, then you have to match the wire correctly. So this one is actually a slightly different one because if you look at this, is folded. So it has a kind of a layer of fold outside the wire. So this one is called the fold twisted pair. So sometimes called FTP. And this one actually is you can see the wires are fold, but then here you also have another layer like what we call braiding. So you have the braiding to further kind of wrap the wires. So this one is called the shield. So this one is the shielded and fold twisted pairs. So there are actually different industry abbreviations for the cable constructions like UTP, STP, FTP, and so on. And as we said, like you can have different combinations of them. Like the one that we saw is, I think that the last diagram that we saw is this one, SFTP. So you have the full twisted pair, and then you have the shielding or braiding outside them. Right. So this one is a quick look of the different quality category of the twisted pairs and also transmission speed and their maximum distance. So then, and in the past, then people have been mostly working on the what we call 100 base TX, right? So that means the 100 base actually just mean 100 megabit per second. So usually these are supported by Cat5 or Cat5e cable or Cat6 or higher, right? So the maximum length is 100 meters. So that's kind of defined by the standard. If it goes beyond 100 meters, the signal will become too weak, right? It will be attenuated too much. So it should not go beyond that. And then for 1000 base T, then the transmission speed is actually going to 1 gigabit per second. And actually, based on the 100 base T standard, we can still use Cat5e cable, or Cat6 cable or higher. So that's why even if you are using like in Hong Kong nowadays for many residential broadband subscription, you can already go to 1 gigabit per second. But even if you are still using Cat5e cable, then that's actually that's fine because Cat5e cable I think when all the 4 pairs are used, then you can get up to 1 gigabit per second. And then your transmission speed need to go even higher, like going to like 10G base T networks. Then you can go for Cat6 or Cat6a or Cat7 or Cat8 cables. So for Cat6, as we said, like this cable can go to 10 gigabit per second, and for Cat8 you can go even higher to 25 or even 40 gigabit per second. And then for the maximum chord length for Cat6 is 55 meters and 6A is 100 meters. Cat7 is also 100 meters, but Cat7 actually has a higher frequency. And also another special thing about Cat7 is it does not use the RJ45 connector. So that's actually it's kind of like a problem because it's kind of not compatible with the older version, like in that sense. And then Cat8 is again going back to the RJ45, so it's more compatible with the previous versions. And then but the maximum chord length is 30 meters only because of the high speed. So in general, I think as you said, like Cat5e is enough for many scenarios, like because like when we are doing the connection, we are just connecting like from our PC or our desktop computer or server to the switch, right? Like at home, then maybe you are connecting with again to connect that to your modem, or then that one again it can support up to 1 gigabit per second already. And also the Cat5e cables are cheaper than the higher categories. So that's why I say most of the time you are still seeing more like Cat5 or sometimes Cat6 cables. Cat7, Cat8 again they are newer, and there's no particular urgent need to replace the older cables with Cat7 or Cat8. Right, so that's why nowadays we are still seeing a lot of Cat5 cables or sometimes Cat6 cable around. Okay, so some of you may wonder why we need to have twisted pairs, why we need to twist the wires like this. Actually, the main reason is that when we are transmitting the signals, that there are a lot of external interference, like for example, what we call the electromagnetic interference (EMI). It can also be affected by other interference like motors or fluorescent lights, etc. So each pair will radiate into the environment, and also each pair receives radiation from the environment, right? Yeah, because they are electromagnetic waves, right? So they will be affected by what is happening in the environment. So signals in adjacent pairs will also interfere with one another. So that's called crosstalk interference. So actually people find that like twisting each pair would help reduce this crosstalk interference. So if you are very familiar with physics, you may know why it works like this. So the crosstalk interference can be reduced when you are doing the twisting, but at the end, for example, at the end when you want to connect this wire to the RJ45 connector, then the interference will become worse because at this point you have to untwist the pairs and put them into the connector. Right, so with no twisting, there is no protection from crosstalk interference. So this is what we call the terminal crosstalk interference. So when we try to connect our wires to the RJ45 connector, we will try to minimize the um the the area where you kind of untwist the wires as much as possible. So we'll try to make sure that the wires are always twisted until the end, until when you need to put it into the connector. So to add a connector, it is necessary to straighten out the ends of the wires to slice them into the RJ45 connector. So as I said, we want to make sure the unpaired part is as short as possible. So one quick installation rule is that we do not want to untwist the wires more than 1.25 centimeters. So usually we try to keep that as short as possible. So now we'll talk about optical fiber transmission. So in optical fiber, so there's a core, which is a thin strand of glass. So mostly used 50 micrometers. And then there's also something called cladding, which is a thin glass cylinder which is on the outside of the fiber optic cable. So usually this one is around 125 micrometers. In optical fiber transmission, so there's a light source of the light of a wavelength of 850 nanometers. So when it goes through the core, so the core is, so in this case, 15 microns. Then you can have like a straight through transmission, and sometimes if the light is not entering this core in a correct angle, then the cladding will provide perfect internal reflection. So the signal will still be able to reflect in here. So when the light rays hit the cladding, they are perfectly reflected in the core and there is no signal loss. So and then when there is the transmission of the light, so as we said, there is perfect internal reflection. But then there is still a problem here, right? So some, like if your light is passing the cables like straight through, right, then you will actually arrive first. But if the light is actually not going in the core, say in a perfect straight through direction, then with the reflection, then it will sometimes we call it the high angle mode. Then you will arrive a little bit later, right? Even though like maybe two signals were sent at the same time, then different modes will arrive at different times at the end. So light rays entering at different angles are called modes. So as we said, that when they are entering in different modes, they travel different distances, and then they will arrive at different times. So this is a very important issue in optical fiber. So it's called the modal dispersion. So if light from different clock cycles overlap, then this will cause errors. This diagram shows an optical fiber cord with two strands for full duplex communication. So these are called the ST connector and the SC connector. So when you have a pair like this, then you can do transmission in both directions. So this is another diagram showing optical fiber. So we can compare the single mode versus multi-mode. So when the core is very small, then basically you run it for single mode only. So you try to make sure there is not like those kind of like internal reflection that we talk about. Right? But then for those when you have a thicker core, then actually what you are doing is you are allowing the different modes to happen. So then this will be the multi-mode transmission. So we'll talk a little bit about light amplitude and wavelength. So for those of you who learn physics in high school, you probably already know this. So light is an electromagnetic wave. So when it travels through any medium, so actually it looks like this. So it's a wave, right? So this one is the wavelength. So it's got the length from the start of cycle to another start of a cycle, right? And this one is what we call an amplitude. So wavelength is the physical distance between comparable points on adjacent cycles. So you can also do it as like a peak to peak. So it's also the wavelength. So as we mentioned earlier, so the wavelength of this light usually used for fiber optic is 850 nanometers, although there are also other standards. So this one is the table showing the optical fiber quality and also transmission distance. So there's OM 1, 2, 3, 4, 5 actually. So this table just compare OM 3 and 4. So OM stands for the optical multimode, which is the standard for multimode fiber. So OM3 actually the minimum maximum distance is 1 gigabit per second. And then for 10 gigabit per second, there's 300 meters. And then for 100 gigabit per second, there's can only go for 100 meters. And for OM4 is much better. So for 1 gigabit per second, so it can be 1000 meters. And for 10 gigabit per second, there's 440 meters. And this was 150 meters for 100 gigabit per second. So by the way, the minimum maximum distance is actually is a little bit confusing, right? But basically it means it has to support at least a maximum distance of say 1000 meters in this case, for example. So if the maximum distance is 2000, 3000, right, then that's fine. But the maximum distance cannot be lower than 1000. So that's what is meant by the minimum maximum distance here. So it's possible to increase the capacity of your optical fiber with multiple cables or multiple cords. Right. So for example, in this example, we have these optical fiber switch. So it's 1000 base SH, which is one of the optical fiber standard. So basically, and you do this, you can do link aggregation. Instead of having one link, you have two links. Then you can have like 2 gigabit per second of your of speed instead of just one. So now let's go back to say the unshielded twisted pair UTP. So suppose you are running the 100 base TX network again with 100 megabit per second. Right? It has a maximum transmission distance of 100 meters. So if the distance is too long, right, it's longer than 100 meters, then the signal will be degrade too much to read correctly. But normally, say within a home, then you don't need to have 100 meters long. But say if you are within a campus or within an office, sometimes it can be very long. So what you can do is actually you can have switches that can extend your distance. So your switch will regenerate the received signal. So it does not merely amplify. So it's not like a signal amplifier. So it will receive the signal and then it will regenerate new signal to pass to the next switch. So if you use multiple switches like this, then actually you can have a much longer distance. So this diagram is showing like you have multiple switches. So you have say this one is a host, then you have UTP to connect to one switch, and then you have optic fiber OM3 fiber to connect to another switch, and then you have this connect to the server with UTP. So in total, so theoretically, you can have a 700 meter maximum data link distance for this connection. So now we'll talk about the data link layer standards for Ethernet. This slide shows an Ethernet frame based on the standard. So it starts with a destination UI48 address with 48 bits and the source UI48 address. So normally for humans to read the UI48 address or the MAC address, so we put it in has a decimal notation like this. And then we will have the tag control ID and the tag control information, which are optional, and the length of the frame, which is 2. And all these three pieces of information in two octets, that means 2 bytes, and logical link control subheader, which is 8 bytes. And here is the actual packet that you are sending. And of course, for internet, then this one is actually an packet based on the IP standard, so it's an IP packet. So and the length could vary, and at the end you may have some padding that you might add if needed, and then finally you have the frame track sequence, which is 4 octets. So now we'll talk a little bit more about the hexadecimal notation. So some of you might know this already, but anyway, we'll go through this. And so in hexadecimal notation, so hexadecimal actually that means 16. So sometimes in short we call it hex. So basically what we do is for every 4 bits we try to connect to 1 digit, such that it's easier for us to read and to see it, right? So it's not too long. So for every 4 bits, if the 4 bits like the 0000, then we change the decimal, that is 0. Then we change the hexadecimal, that is also 0. Right? So basically the first step we do is we convert this binary number into decimal number. So then for these numbers here, then actually they will become 0 to 15 in decimal. And then for converting that to hexadecimal with base 16, is for 0 to 9 they are the same. And then 10 will become A, 11 will become B, 12 will become C, and then D, E, F respectively for the remaining numbers. So that's why you can represent 4 bits in 1 digit, right, when you write your MAC address in hexadecimal. So it's much easier for people to read, as we said. So just some quick questions here. So for example, what is 0101 in hex? So you convert to binary. So this one is 1 plus 4. Right? So it's 5. So it's just 5. And then 0000, that is 0. Right? And 1001. So this is 1 plus 2, 4, 8. Right? 1 plus 8. So it's 9. So in hex is also 9. And then 1111, that is actually 1 plus 2 plus 4 plus 8, which is 15. So in hexadecimal, that is F. So to convert a 48-bit MAC address to hex, first we will write down the 48-bit address in 12 4-bit nibbles. So a nibbles means a group of 4 bits. And then you represent each nibble as a hex symbol. And then you pair the hex symbols and put a dash between the 6 pairs. So we can try, for example, try these 4 nibbles. Right, so 0000 is 0. 1111 is F. And 0101, and this one is 1 plus 4, so this one is 5. And this is 1010, so it's 2 plus 8, so it's 10, so it's 8. So this one actually will become 0F58. So just a quick exercise. So if I want to convert this EUI48 address to binary, then we actually have to do this one by one, right? So then of course with the table that is actually quite easy to do. So I'll just quickly talk about the answer, right? So A will become 1010, and then 0001, and then this will be 1011, 0010, 1100, 1100, and then 4 will be 0100, 0100, and then this one is 0101, and D will be 1101, and 3 will be 0011, and finally C will be 1100. And say if I want to convert 8F to hex, then no, actually 8F is already has. Actually, we should say we want to convert 8F to binary. Then 8 would be 1000, and then F would be this 1111. And then if we want to convert 1001 to 0101, there will be 1001. Then you think about it, this one is 9, right? 1 plus 8, this is 9, and this one 0101 is 5. So this one will become 95 in hex. Now let's go back to the frame. So after the destination and source addresses, then we have the tag fields, which are optional, and they are for priority and other matters that are not in the original specification of AO 2.3. So in general, there are 3 bits in the tag control information field that are for priority level. And then here, the length field contains a binary number, and the maximum length of the data field is 1522 bytes. And then we have the logical link control subheader and also the actual packet. So this one is actually what now we have as the data field that we are sending in the frame. So you set the packet, and this one is the IP packet, and the logical link control subheader is actually kind of like a sub layer in the data link layer here. The purpose of this LLC subheader is to describe the type of packet contained in the data field. So finally, after the packet, then we have some padding to make sure that it's actually aligned well. And then finally, we have the frame check sequence, which are 4 bytes for error checking that we have talked about in previous chapter. So now we'll look at some multi-switch Ethernet operation. So we know, for example, if this computer here want to send a frame to another computer here, so it may have to go through multiple switches. So a packet will go from this computer to switch 1, and then to switch 2, and to switch 3, and then it will go from here, right? It will go here. So it must pass through the different switches. So the question is how the path is decided. So as we talked about in earlier chapters, actually the switch actually will have a switching table. So for example, after switch 1 received the frame from this computer, then you will check the switching table to see if the destination, if this E5, BB, and so on. So it will look at this switching table and see for this address that where I should send the frame to. So in this case, so it should send out port 5. So send out through port 5. And port 5 on switch 1 is connected to port 3 on switch 2. So then this frame will be sent to switch 2. And similarly, then switch 2 will have a switching table, and then you will follow what is there. So after checking the switching table, switch 2 find that it should send the frame to E5, that E5 computer out the port 7. So again, each switch has its own switching table. So you know, I will just send it to switch 7. Port 7. So it will send out, and then you will arrive at port 4 on switch 3. And then switch 3 will check the switching table, and then you will find that it should send the frame to E5 out port 6. So out of port 6, then you will send out the frame, and then you will arrive at the computer E5. So that's how a frame will travel through multiple switches, and the core idea here is that each switch will have its own switching table. So now we'll look at some more advanced switch operation. So the Ethernet standards actually require hierarchical topology of the physical organization of switches and the transmission links. So it will be hierarchical. So you have a high level switch, and then you have a second level, and then you have the host, or you can have more levels, but basically it must have a hierarchy there. So if you are structured like this, then actually there's only one possible path normally for any two hosts, right? You must basically go to the highest level shared switch among these two among any two hosts, right? And so normally there's only one path is hierarchical. So later on in chapter we'll actually talk more about this a comparison of Ethernet switching and IP routing. So in IP routing actually is much more difficult because the routers are not arranged in a hierarchical way, so there can be multiple paths going from, say, one device to another device or one computer to another computer. There are many possible routes that you could take, so that would be more complicated. But then for Ethernet switching, if it's hierarchical, then it's relatively easier. So the problem of this hierarchical setting is that there are many single points of failure. So if there's, say, a problem with switch 2, then this one is actually a single point of failure, right? Then any computers here would not be able to talk to any computers here under switch 3. Right? So and similarly, if switch 1 is not working, then all actually computers connecting to switch 1 are also in trouble. So you have this many single points of failure in a hierarchical network. So that's why some of these setting, like for example, based on the IEEE 802.1W, they also have the backup link and rapid spanning tree protocol. So that means commonly can install a backup link between switch 1 and switch 3 here, and then normally the rapid spanning tree protocol RSTP would disable the backup link. So the link is there, but normally it's not used because loops are not allowed in Ethernet and a strict hierarchy is required. But there is a backup link there. So in case when switch 2 fails, then this backup link will be used. But otherwise it's just a backup and not used. So when switch 2 is not working, then RSTP will activate the backup link automatically. And then this computer can still switch these other computers here. So there are also some other advanced Ethernet capabilities that have been proposed in recent years. For example, priority can be set in the Ethernet frames. So Ethernet switches actually can provide up to 8 priority levels. So different priority can be given to different frames. And then you also have manageable switches that can be managed by SNMP that we talked about in previous chapter. Is a simple network management protocol. So although manageable switches cost much more than non-manageable switches, it's more than make up for by lower management costs. As you say, you can control all these devices centrally and remotely, and also much more easily than those like non-manageable switches. So software-defined networking may also bring a revolution in switch management. So another capability is power over Ethernet that also has gained some attention and also some application in recent years. So because if we talk about the copper wire, actually they can also carry electricity, right? Because the signal itself are electricity, right? Yeah, it's basically electrical signal, right? So which is actually can supply power to devices via the UTP, right? Because as I said, they can carry electrical signal. So it's just like very old school like telephone system, like wire telephone system actually also get the electricity through the wires. So that's why you don't need to have another like electricity plug for your traditional telephone. And also USB ports are actually doing the same thing, right? You actually through the copper wire through basically through the UTP, you can actually pass the power. So it's much less expensive than supplying power separately. And so you can like some of the devices actually can get the power from the switch. So in that sense, the switch also become a power supplier. So that's what PoE can do. So we also have PoE Plus. So USB ports provide both data transmission and power to hosts, and then switches actually can do the same thing, right? If for switches implementing PoE Plus, they can provide up to 25 watts of power over UTP to host. So this is actually sufficient for many applications like voice over IP phones, surveillance cameras, and also many access points. So this will save money because there's no need to install power lines to these devices. You need to install power lines, and that's actually a separate line, right? So that would be much more expensive. So of course, like if we talk about 25 watts, they are not sufficient for desktop or laptop PC. Usually you will need at least like 200 watts, right? So these are for good enough for small devices, and also as we said, some applications, and we are already seeing some use of power over even Ethernet in recent years. So finally, in this chapter, we'll talk about Ethernet security. So there is a standard for Ethernet security. So that's the 802.1x. So it's they have the port-based access control on Ethernet switch. So the problem that it's trying to address is that anyone actually can enter the building and plug their computer into a switch or into a wall RJ45 port, right, which connects to a switch, because actually all the wall ports that you are seeing, right, then there must be a cable behind, otherwise the port will not be working, right? So usually that cable is connected to a switch, right? So that means everyone can kind of plug into your switch freely if they can physically enter your building. And these kind of things are very difficult to stop, right? For example, imagine on campus you can easily plug into any wall jack. And also when you like if you are a visitor to a building, to an office, and usually you can find some chance to plug your cable into a wall, right? So then this usually gives the attacker access to the network without going through a firewall. So depending on your setting, right? Some setting actually um, will, most of the time when you do this, you bypass the firewall because you are already in the network. Right? You are already directly connecting to the switch. So that's why people came up with this protocol or the standard for port-based access control. So the idea is we would want to have access control at switch ports. So based on this 802.1x port-based access control, so it's created by the 802.1 working group. So it's not by the 802.3 working group on Ethernet. So as you said, 802.1, then these are for more general standards, like security standards that can be used by different groups. So the idea is, so if you try to plug into this kind of wall jack, and then it's connected to a switch behind the wall, right? Normally, so the supplicant must authenticate itself before it can use the port to which it connects, right? So then you will go through a central authentication server. So then it will have an authentication database, and then it will check whether the say username password provided by the supplicant are correct, and then they are all, and this person is authorized to use the network. So based on 802.1h, then you can prevent this kind of hackers to connect to your network so easily. So authentication data is stored on the central authentication server here in the database. So it's also much easier to control, right? When you have multiple switches, then they are all checking in this central authentication server instead of having like multiple servers. So there are some advantages of a central authentication server. So you have consistency. Attacker cannot find a misconfigured switch, right? So if you put the authentication at the switch level, then if the switch has problem, then the attacker can still hack into your system. But if it's based on central authentication, then as long as you make sure the central authentication server is working well, then you don't have problem. You can also apply rapid changes easily when someone leaves your organization, for example, retired or basically resign, then want to go to another company, and then you can update that person's username and basically the rights immediately just by changing one piece of information on your server instead of having to go to multiple switches to make all changes one by one. When you have a new employee, it's the same. You just need to add the new username password to the server. Also, the switch cost will be different. Basically, it will be lower because the authentication server will be doing the heavy work, so there will not be a burden on the switch. And also you have reduced management costs. Only one authentication server on a database that have to be maintained, and you don't need to maintain all those switches by having like all these password username to be updated one by one as mentioned earlier. So this one is an example of one possible attack to the Ethernet is man in the middle attack using ARP poisoning. So ARP is the address resolution protocol. So ARP cache actually tells a host where to send a frame to reach a particular IP address. So the correct ARP cache may be like this, right? So you know if I'm sending to IP 1234, then the MAC address is this one. So then the attacker actually is trying to poison this ARP. So this one is where we want to send the frame to. IP is this, and the URI address is AABBCC and so on. So normally then I will be able to send without problem if this ARP is correct. But if the attacker is able to poison or kind of to change the ARP cache without being noticed, then actually you can do this what is called the ARP poisoning attack. So now it's saying 1.2.3.4. This IP address actually have the MAC address as FFFFFFDD and so on. So instead of the true MAC address. So if the attacker has successfully done this, then when the victim send the frame, then you will be sending to the wrong address. So right now when the victim is trying to send this frame to the default router, then you will go to FFFFFDDDDD instead of the actual router. So this one is really the address of the attacker. So the attacker will get your package. So this one is the man in the middle attack. So the packet will go to the attacker instead of going to the intended destination. So many Ethernet networks actually are wide open to these ARP poisoning attacks. So the AO2.1 working group actually has developed a general solution. There is the AO2.1AE standard, which requires hosts and routers to authenticate the source of ARP messages and also other messages before the receiver will accept them. However, the standard is not widely used. So that's why in the future, if you get a chance to manage Ethernet, you need to be careful about this kind of ARP poisoning. Okay, so that's all we'll cover in this chapter. So see you next time.